Yes.
I'll bring you a whole pack tomorrow.
Okay. I circled it. What's this one called?
Rose.
Rose.
Oh, I got
The one below, what's that one called? Rose. The one on the right, what's that one called? Limason with a loop. Limason with loop. Beautiful. And what's this one called? Heart. It is. It's a limason as well, but it's a limason with this very special name. This one's called a cardioid. Do you want to know why it's called a cardioid? What does that look like? It's like a heart. It's like your cardiovascular system, which is the heart and blood vessel system. So, vascular system. On we go. Forget this one. Go to your notes in 6-5. And you guys have a problem, page 8. Abran sus notas a la página 8, por favor. R equals 4 sine 3 theta 8. 6.5. It's after page 7, before page 9. In your notes. Do you need notes? Is that what you mean?
Okay.
Okay.
Really funny vibe.
That was my. You guys did a ton of stuff with this last week. Roses. By the way, this is a rose. We'll start with rose. Everything's coming up roses. This, what did you guys learn about, like, that number? Let's say that's called R equals A sine N theta. What did you learn about N? Yes, ma'am.
That when it's an even number, the number of petals double, and that when it's odd, it's the same number.
You got it. So N is even, petals equals 2N. Done. Circled that. Good. That's what you learned. I like that. And when N is odd, you want to give the contrary to that? The petals
Same number.
equals N. Cool. Really helpful. Good. You discovered that on Friday. We're going to adopt that into our consciousness because it's super important. We also learned about A. Do you remember what A represented? If you don't, that's okay. A was, let me pull up a little picture here.
A was the radius of the petals, or the distance.
Yeah, so what it turns out to be is it ends up being the maximum distance. We're doing 4 sine 3 theta. And there's our little petals. There's 3 of them. It has an orientation, which would be different from if I put it in terms of cosine. So why don't you guys take a peek at my cosine version and see if you can come up with a good reason what the difference is on that. Okay, what's the difference between sine and cosine? Green is the sine curve. They're like, is it the same shape?
Rotated 90 degrees.
Rotated 90 degrees, so I twist it 90 degrees. So it looks like it's twisted 90 degrees. That seems reasonable. Does that seem reasonable to you guys? Or negative 30, any others? It's kind of hard to tell. What's that rotation that happens? Huh. It's hard to pick up on the rotation, but I'd say it's somewhere in there. You could do it negative one way, positive the other way. More importantly, actually, what we focused on, and if you remember your notes, it wasn't about rotation. It was about, does it have even symmetry or symmetry about the y-axis or symmetry about the x-axis? And to answer that question about radius, by the way, you're right. So Abe, if it's 4 is that A value, that's the length of the petal. So we actually just call it petal length. Another way to think of it is it's the maximum radius because it never gets bigger than that. Think of what 4 times sine of theta could be. Sine has a limited possibility. Sine can only be 1 and negative 1 at its maximum. So we're talking 4 and negative 4 is the biggest our radius will ever be. So it's the maximum radius. That's another way to think of it. Max radius, petal length works as well, because the petals will be the biggest. Cool, that's what you picked up on. We're going to go to your pictures on the next couple pages and just take a second to try and just go through a number of them, and then we're going to write characteristics underneath it. It doesn't take too long. So let's knock those out of the park. The next thing I have on here is this odd-even business. Or not odd-even, it's more about the symmetry again. It's easy to tell symmetry about the x-axis. So let's see which one is which. If I go back to my drawings on here, which has symmetry about the x-axis? Is it cosine or sine? Cosine is the x-axis. It's the blue one. You're very correct. So we go to cosine. X-axis symmetry. It seems that my cosine curves have that x-axis symmetry. It seems. I'm going to put a question mark there until we disprove it. The y-axis symmetry then on the flip side is, does the sine curve in green have symmetry about the y-axis? It does. Everything is on left and right is the same. So let's go ahead and just say it must be, is it the sine curve that is y-axis symmetrical? And about the origin, we'll have to check it out. Next little slide that I have is let's prove that 4 sine of theta is symmetric about the y-axis because it's a sine. We know that it seems that sine is symmetric about the y-axis. There's a way to prove it by this table on the other side. To prove y-axis symmetrical, if we input negative r and negative theta, your function that you're inputting into stays the same. And it's your polar graph, polar equation, stays the same. That's written up above too. But that's the idea of having symmetry about the y-axis, is that we're going to put a negative r and negative theta into the polar equation, and the polar equation will stay the same. That's the test. So if I do it down here, we're going to take out that r and we're going to put in negative r. We're going to take out that theta, we're going to put in negative theta. And using the identities that we know and love, we should get the same function. And y'all remember about sine of a negative angle? Anything about that, like ring a bell? Sine of a negative angle? Way back when? Totally negative, so it's same as negative 4 sine 3 theta. So sine of a negative angle is like negative sine of a positive angle. Okay, so we use that identity. Then what do you guys know about if there's negatives on both sides of an equation? They cancel. Or you can think of divide both sides by -1. So these are gone, gone. We have the original. So we know this. So we've proven there's y-axis symmetry. If you put those given values in, okay, in y-axis symmetry, if I actually look at the graph of it, what it's saying, if I turn off, this is the one that we did, the sine version, go away. If you take and put in a negative angle, like go the opposite direction, a certain amount, and then you do a negative radius. So think of whatever gets you to this point right up here in the upper tip of that first petal in the first quadrant. If I use a negative radius in the same amount and then do negative angle in the opposite direction, then do a negative radius, I land in a mirror spot on the other side. If I think of this little petal in the bottom facing down, that's from going 270 around. Okay, so that'd be a particular theta from looking, or actually that's from looking pi over 2. So whatever theta you have, if you go negative that direction and then do an opposite radius, you'll land on its mirror image on the other side. So that process, if you want to do it piece by piece, works out. Don't want to say much more because the next thing I need you guys to prove is actually right now. We're going to talk about domain range and max values. You have on your sheet this domain thing. Let's clarify something. I got to look at this graph. Negative infinity to infinity. All right, I just got done looking at this thing. The domain does not look like negative infinity to infinity to me. Except it's different. Domain is the possible input values, and our inputs are not x. So you have to differentiate between, this is polar graphing, this is for input theta. and we can put in any theta we want. Domain is input possibilities. Range is output possibilities, and our output possibilities are from, now you look on the sheet, it says from negative absolute value of A to positive absolute value of A. And what that means is that's our radius, our max radius value. Our output is in radius terms. So range is possible outputs. It's not Y's, it's possible outputs. So just be careful. Our radius can go from -4 to 4. Flip it on over. Keep on rolling. I think the rest is self-explanatory. We already talked about the n is odd, n is even. Thanks to Sydney, she summarized that for us. We don't need to dive into it, but it's in your notes. Down below, the maximum R value in this lovely picture, you're going to tell me in just a minute because we're going to graph these. So you guys did a great job graphing these. We'll play with our calculators in a minute. But I want to graph on this for as much as possible, just to catch up with Friday. R equals 2 plus 2. This is the... Let's go with limicons. My notes are in backward order. So you guys go down, this is in the limicons section on your notes, way down on the bottom of page 9. We'll go back to roses in a minute, but it applies to roses as well. So it's not completely off base. Okay, so next, 2 plus 2 cosine of theta on that next piece. This is just to talk about our general shapes and what you guys noticed. What did you guys find out about 2 and 2 cosine of theta? Let's stick with cosines for a little bit. What if I make it r equals 3 plus 2 cosine of theta? Okay, what did that do to it? What if I made it r equals 4 plus 2 cosine of theta? You guys played with this the other day. What kind of generalities did you come up with for that? Isn't that crazy?
It has to be less than 2 to have an indent.
Yeah, it seems like, oh, less than the 2 to have an indent. So, like, if it's going to indent like it did in the orange one,
Yeah.
it didn't end up being less than 2, but those... what do you mean by less than 2? The indent one is orange. It looks like an orange too.
Well, like the integer in front, the 2, that one.
Yeah.
It has to be less than 2.
Well, it's actually currently equal to 2, and it's
Well,
making...
like equal.
Okay. So like equal to this one. So this one's
like
equal.
Try, like 1 plus.
Okay, let's do 1. Good idea. Because we need to figure out what that other side. 1 plus... Oopsie, got my R. R equals 1 plus... I'm getting there. Mr. Incompetent... Oh, I'm about to get frustrated. Yeah. I can do it. Oh, okay. Isn't that weird? I have here's my this is what I look at. You want to see my crazy thought on this one? It's like gravitational pull. This number, the larger it is, the more gravity it has to suck this dimple or loop out. So if this number is equal with this one, they touch at the origin. But if I enlarge this number, it pulls that dimple or that cusp away from the origin. If I make it even bigger, it pulls it further away. If I make it 5, it'll pull it away further yet. I think of this outside number here as the thing that sucks it away from the origin. It pulls it away. The inside number inside here, like this 2 right here, if this number out front doesn't have enough power to suck it out, look what happens. It goes in the other way. It's like a gravitational pull. It's like pulling on this, but it's so weak that it got beaten by this one and it got sucked inside. Isn't that crazy? It just helps me because I don't have to think about them anymore. I literally look at that and go, oh yeah, it's going to touch the origin. Oh, more powerful, it's going to be out a little bit with it's going to be a dimpled limicon. Ooh, it's way out there. That's going to be a nice convex limicon. This one here,